Hello there. Today we have a very special problem about electromagnetism. And it's a problem that a lot of students have a lot of trouble with. And it's also a very common problem that pops up in a lot of IB tests. If you see the previous sections in this chapter, you will also see that we have studied how a charge moving through a magnetic field will experience a force that's perpendicular both to the direction of movement and is perpendicular to the magnetic field. This is a bit different than that. Here we have a rod instead of a charge, which is moving at velocity v through a magnetic field B. Also, it's connected by two conducting rails here, which connect to a resistance R. What the question asks for is the power P needed to maintain a constant velocity. So let's understand what's happening here for a moment, right? So what we know is if it were a charge, it would move in this direction, which by the right-hand rule, and there's a magnetic field going inwards. So the force must be upwards. So the positive charges are being forced to the top. Also, the negative charges are being forced to the bottom. Normally, if this wasn't all connected, then the charges would go nowhere. But because it's connected, the charges will travel through this wire, through the resistor, and back, causing a current. Of course, also because there's a current that's running through a resistor, there's a loss of energy, which is why you need extra power to maintain the constant velocity. Now that we know what's happening, let's see the equation that we already know, which is the force exerted on the charge is equal to the charge times how fast it's going, the velocity, times the magnetic field. But this is not quite what we need. If there is a resistor and there's a current, in order to get the power, we need to find the voltage and we need to find the current. If we rearrange this a little bit, we can also find that the power is equal to the voltage squared over R. But we still need to find the voltage. Now, there is a way to change this equation so that gives you the voltage. And the first step is, if you look closely, the L here is not in this equation. So if you multiply both sides by the length, you'll get LF times QLB in this manner. You also see that force multiplied by distance will give you energy, right? So this factor turns into E equals Q V L. Now, the reason for this is that if there's a charge in this rod, what will happen is by moving through this magnetic field, the charges are forced upwards. And the distance there's forced upwards is the length of the rod. So every charge that is in this rod will experience a force and we have a certain amount of energy. Right? Now we have this. But it's still not quite what we need. We need to find the power, not the energy. So we divide energy by the time and divide this side by the time. And you will know energy divided by time is equal to the power. Right? But in this side, we already have the velocity, we have the magnetic field, we have the length. We don't want to mess with that. So what we need to do is, what is charge divided by time? And you know that charge divided by time is the current. V, B, L. We're almost there now. So we take this, the current, and the current divided from both sides will give you, in the right side, just the velocity, VL. But the current divided by the power, according to this formula, is just equal to the voltage. Big V, not to be confused with the velocity. And now we're almost there. Remember that the power was voltage squared divided by R. Here we have our voltage. All we need to do now is the voltage squared will be the velocity squared times the magnetic field times length, both of them squared, divided by the r. And there you have the answer to this question.